Okay, so this is a synthesis problem. We're going to start with the keto ester on the left. And look, if you've watched the other one, there's a tricky one where you get a cyclization, right? These two are very far apart. The ketone and the ester aren't going to interact in any way. Okay, so the idea is you turn the molecule on the left into the molecule on the right, using as many steps as you want. You can use some other reagents, but all these carbons, all the aromatic carbons, this benzene has to be that benzene. All right, hit pause, go work it. I'm going to launch right into it. Okay, you're back. So if you didn't use a protecting group, you should hit pause and try it again. Okay, so you have to use a protecting group in this synthesis. So if you didn't, hit pause, try it again. Okay, so you're back. I hope that you're going to have used a protecting group. Now, what I'll say is, in any synthesis, you want to look at what changes. The ketone doesn't change, right? This methyl ketone stays in place. Okay, so cool. Don't do it. You don't have to do. You think you don't have to do anything there, but you do change here. So we're going to break the carbon-oxygen bond to the methoxide, and we're going to add two methyls here. So we have to make that bond, and we have to break that bond. And I hope at this point, or at least very soon, that you can tell that an ester, right? So if you treat this ester with two equivalents of methyl Grignard, you'll get what you need. That makes the transformation, right? So if I take an ester like this, two equivalents of methyl Grignard, I'm going to get that plus OCH3 minus, right? And then you protonate and you get what you need. And the way this works is the methyl adds in, get your tetrahedral intermediate, your methoxide is there, methyl is there. Methyl minus is not a leaving group under any conditions. So the O minus in the tetrahedral intermediate is going to kick out methoxide. That'll give us a methyl ketone. And now the second equivalent of methyl Grignard adds in to get us up there. Okay? So the way to turn this ester into this gem dimethyl alcohol is two equivalents of methyl Grignard. So you think, cool, I'm there, I've got it. But methyl Grignard is going to add to the ketone first. All right, ketones are a little more electrophilic. Methyl Grignard is at least going to add, they're probably going to be pretty competitive. There's no real way to add methyl Grignard here and not there, or vice versa. So that's where I say you have to protect. We have to protect the ketone. Okay, so we have to somehow block this from happening. Okay, so I'm going to erase all this blue stuff. If you want it, hit pause and write it all down. Okay, so the way to protect a ketone is by making an acetal. And typically we would use a cyclic acetal. And so this is chapter 19, I think. You're going to have to remove water. You're probably going to reflux this. You're going to use ethylene glycol or maybe propylene glycol, catalytic acid. And the product you're going to get. So here we take advantage of the fact that ketones are more reactive. So we can make the acetal on the ketone and it won't touch the ester. And you can find conditions. You could certainly make this reaction react on the ester, okay? So catalytic acid, this would be a transesterification. But do this at 25 degrees and you monitor the reaction by TLC. The ketone's going to react a lot faster than the ester. So we could make this react. We could make the ester react with ethylene glycol under acidic conditions. But we don't want to. So you can differentiate that. That is now an acetal. It's a protected I should really try to write level, right? That's a protected ketone. Okay, and now we hit it with our two equivalents. So first 2 equivalents of methyl grignard. Second, weak acid, a weak proton source. That gets us our, sorry, it's been a few days. My board management is off. So this gets, we've now converted the ester to the gem dimethyl alcohol. We still have our acetal in place. Right? To get the ketone back, it's, remember, acetal is hydrolyzed with aqueous acid. So to deprotect, H3O plus. And you can actually make the second step here and the deprotection step the same step. You can just say, we're going to hit this with H3O plus, the acetal will fall off, we'll protonate the alcohol. So this is the deprotection. Okay, so one more time, let me go through the protection, the idea of a protecting group. We've got 2 functional groups that will react with the necessary reagent. We have to use methyl grignard or methyl lithium or something on the ester to turn it into this gem dimethyl alcohol. Okay, so the ketone is going to react with methyl grignard. There's no way to stop that. So if it's a ketone and we add methyl grignard, we're going to get a methyl group there. We'll actually get the same functional group here as we would on the other side. Okay, so I'm sorry, I just thought of a way you could do the synthesis that would be, nah, it wouldn't work. Never mind, it won't work. Okay, so we need to protect the ketone. And you just change its functionality in such a way that it won't react with the Grignard, but that you can get it back. And the way we do this for ketones and aldehydes is we make acetals. So you could use methanol or ethanol, but you can also just use ethylene glycol, make a cyclic acetal. Those are nice and stable. Catalytic acid, drying agent. We monitor this until it's done because we don't want the ester to react. So now the acetal, right? You can't do SN2 on a tertiary center. O- isn't a good leaving group. We're not going to break a CO sigma bond in an SN2 reaction. So we call this a protected ketone. It's in the oxidation state of a ketone. We can get it back by hydrolyzing with aqueous acid, but it doesn't react like a ketone. Then we do our Grignard. The Grignard adds twice to the ester. Grignards are always going to add twice to the ester. We protonate, get our alcohol, that sets this group, and then we convert the acetal back to the ketone just by an acetal hydrolysis. So the protection step is making the acetal, the deprotection step is hydrolyzing the acetal.